Good morning, everyone. Today, I will try to explain the research work we have done, and I will also show you some of the results that we have achieved. But first things first, my name is Angel, and I'm currently working on my PhD thesis about cybersecurity. And today we're going to talk about cybersecurity evaluation for embedded systems, and more precisely about security metrics. Here you can see the table of contents of the presentation. First, I will introduce the problem that we want to solve, and I will give a little bit of context. Second, we will talk about the previous work done, and then we will comment the contributions that we have done, and finally the conclusions that we have extracted, and the future work that we propose and we plan to do. So let's start giving some context and explain the problem that we want to solve. Today, embedded systems have become the driving force behind technological development, with a strong presence in sectors such as manufacturing, transportation, energy, telecommunications, healthcare, and defense. So proving to be a key piece in the industry whose importance is growing. They are everywhere, and not only that, they also control critical processes and information. They are growing in number, and they are also connecting to each other and to the internet. So under this scenario, there is an increasing number of security threats over embedded systems. But in embedded systems development, security is not a priority in most cases. So embedded systems must be protected, but how can we know if an embedded system is secure enough? As I said before, there is an increasing number of security threats over embedded systems, and countermeasures are being applied to protect them against known threats. As such, there are some questions that arise and cannot be answered yet, such as, do countermeasures work properly? Is there coverage enough to undermine threats? And are those countermeasures correctly implemented? In this situation, a standardized and general accepted security testing methodology is needed to provide guidance, confidence, structured procedures for the testers, common reporting forms, and the possibility to compare results along the time and among different systems. And we think that these last factors can be achieved by introducing security metrics into the evaluation or the assessment process. Furthermore, if carefully designed and chosen, metrics would provide a quantitative, reproducible, and repeatable value that would reflect the level of security protection of the embedded system. These metrics can put some light on measuring the degree of confidence in the effectiveness of the implementation of security measures in an embedded system. Metrics would allow the comparison of different evaluation of the same device over time, and even evaluation of different versions of the same device or the comparison of different devices. I think that our approach is really well expressed with this quote from Lord Kelvin, when he said that when you can measure what you're speaking about and express it in numbers, you know something about it. So this is more or less a fancy way to say that we aim to use security metrics as a key piece to assess the security level of embedded systems. And now we are going to explain the previous work done. As you can see in this slide, the research work that we have done can be classified into 5 main topics, and now we are going to take a quick look to each one of them. We analyzed the main security standards to check whether they proposed any kind of security metric. So the IEC 62443 for industrial cybersecurity proposed conformance metrics for managing a security program throughout the life cycle of an industrial automation control system. On the other hand, the common criteria defines the evaluation assurance levels, the EALs, as an increasing scale. The highest levels mean that more testing was done, but not necessarily that the product is more secure. The NIST defines 9 security metrics for 3 different aspects, but it addresses security at a very high level, the organization level. And finally, the OSSTMM or OSTEM proposed a scale measurement of the attack surface. Although there are a lot of approaches proposed in the standards, most of them address security at a very high level, so they can be applied to embedded systems. We have also checked for the main issues of security metrics, and we found that there is a lack of solid theoretical foundation in support of the claim correlation. So this means that the property that we want to measure with our metric and the result that we obtain with it not always is related, or at least the relation that they have is not as solid as they claimed. We have also identified that there is a lack of scale, unit, and reference values for comparing and interpreting the results. There is also a lack of available implementations, and there is almost no benchmarks for comparison. And finally, of course, there is no widely accepted solutions. With all these problems, it is difficult to understand whether they are applicable in a given context, the metrics that papers proposed, and how to use them. We have also reviewed the literature to find which are the properties that a good security metric should fulfill, and we found three main criteria. The first two criteria are the SMART and the pragmatic criteria, where each letter represents a different property that the developed metric should meet. Here in this slide, you can see the definition for each letter. And finally, the third one are the properties identified by Savola carrying out an expert survey. He interviewed 141 security experts from 21 different countries. He tracked 19 quality criteria. Savola identified correctness, measurability, and meaningfulness as the main quality criteria, along with usability. On the other hand, we analyzed the literature to find which metrics can be applied to embedded systems. In order to do that, we did a systematic review of the literature, and we found more than 500 security metrics. After filtering them to discard all the security metrics that couldn't be applied to embedded systems, we reduced the list to around 150 security metrics, and we planned to choose a smaller set of metrics to apply them to evaluate a real embedded system that we are going to use as a reference device. If you want to access to the whole data of the metrics that we have analyzed, you can go to the link below. And finally, we analyzed the literature to find the most common taxonomies that are usually used to classify security metrics. We found that the most common one divides them as follows: organizational security metrics that are used to describe and track how effectively organizational programs and processes achieve security goals; technical security metrics to describe and compare technical objects, for example, algorithms, specifications, and architectures; and finally, operational security metrics that are used to describe and manage the risk to an operational environment. We realized that taxonomies proposed in the literature, the ones that we found, are designed at a very high level, usually at an organization or network level. So they cannot be applied to classify metrics that assess the security level of an embedded system. After all the research work that we have presented and taking it into account, now we are going to explain our contributions to the state of the art. The first contribution has to do with the properties that a good security metric should meet. We compared the three main criteria found in the literature to find the common points among them. A mapping, that you can see here in the slide, was carried out using the definitions and the data given by the authors. Here, each black dot you see is a common point between two properties of two different criteria. As you can see at the top of the slide, The properties that Sabol identified as the most important ones are correctness, measurability, and meaningfulness, and of course, cost is expected also to be a relevant criterion. But in our research work, the properties that we expect a metric that is going to evaluate the security level of an embedded system are comparability, cost effectiveness, measurability, repeatability, and reproducibility. As far as the analysis of the metrics is concerned, we classified all the metrics that we found according to the asset of the embedded system that they evaluate, and we found that an interesting, albeit not very surprising fact is that most of the metrics, 77.5% of them, were related exclusively to software, while on the other hand, only 0.6% of them were related exclusively to hardware. This shows that there is a clear lack of hardware security metrics in the literature, and main efforts are centered in developing software metrics. It is worth commenting that these metrics are not only valid for embedded systems, but they could also be applied to other systems. And finally, we proposed a new taxonomy for classifying security metrics. To the best of the author's knowledge, there is no taxonomy that focuses on the specific assessment needs and limitations of embedded systems. Unlike other proposals in the literature that are at a very high level, this one is specifically designed to evaluate all aspects that comprise embedded systems. Here we divide them as assets that are the elements of embedded systems that can be evaluated, such as hardware, software, or data, security dimensions, which attribute is to be protected, and finally metric properties, which are the characteristic parameters of metrics, such as is it possible to automate that metric, or how much that does it cost to compute the metric. And it's really important to notice here that metric might cover more than one asset and more than one security dimension, but at least one value for each one has to be assigned. This is showed as a dashed line in the figure. Nevertheless, all values in metric properties are needed for each metric, as they represent the way the metric behaves, the cost associated to a metric, and the information it returns. And this is represented using solid lines in the figure. And we think that the best way to understand how this taxonomy works is using an example. So here in this slide, you can see an example of applying our taxonomy to the side channel leakage metric. This metric uses a statistical test to measure if a device is prone to a side channel attack by comparing two sets of data, a random one and a fixed one. So this metric is evaluating the hardware of our system. It is related to the data confidentiality, and the properties that this metric has are that it can be obtained using semi-automatic tools. It returns a nominal result, so it leakages some information, or our system does not leak any information. It has to be evaluated while the system is running, so it's dynamic, and finally the computing cost of this metric is constant. With all this, finally, and to finish the presentation, we will briefly comment the conclusions and the future work that we plan to do. As conclusions, we can say that security metrics are not standardized, and they will help in quantifying the security level of embedded systems. This research work proposes a new taxonomy for security metrics, which takes into account the different assets of embedded systems. A conceptual mapping of criteria for choosing most appropriate metrics is also given, and the metrics that we can apply to embedded systems have been identified, and we realize that most of them are related to software. And finally, as future work, we are planning to choose a smaller set of metrics, refine them, and apply it to a real embedded system. and we hope that this work will be the foundation for proposing a security assessment methodology specifically designed for embedded systems, which will provide qualitative and quantitative results. Thank you very much for your attention.